Start by acknowledging that this talk takes place on the unceded lands of the Wurundjeri people of the Kulin Nation, and pay respects to their elders, past and present. Our speaker today is Haomin Chen, who will be telling us about LBA models of confidence and response time, and I'll pass it over to you. Thanks.
Hi everyone, I'm Haomin. So today I will be talking about different types of models of confidence and response time within the linear Ballistic Accumulator framework. So first of all, I want to acknowledge the co-authors, Professor Andrew Hisker, Dr. James Sauer, Dr. Matthew Comer, and Dr. Evan Osth. So a lot of works have been interested in the relationship between confidence and accuracy, or between response latency and accuracy in decision making. However, a few of them have looked at how these three measures can interact with each other. And a lot of computational models of accuracy tend to focus on confidence, but not latency. So the question we ask here is that, how can we use a unified framework to account for the complicated three-way relationship among confidence, response latency, and accuracy? To get to the answer, we broke up this big question into some small ones. So the first one is, how exactly do people make confidence judgments? So researchers published a paper in 2009, which beautifully demonstrate a range of ways that confidence can be constructed. On one hand, confidence itself can be directly accumulated. This represents the idea that confidence is essentially a multi-alternative decision-making problem. It's almost like you're choosing between those confidence options. So recurrent status response time and confidence models is an example that captures this idea. On the other hand, confidence can be products of other processes. For example, it can be derived from a comparison of evidence strengths between choice alternatives, as described by weakest balance of evidence model. So this one can then represent the idea that if you have a lot of evidence for one alternative, but not so much for the other, then you are probably very confident. But if you have equal level of evidence for both, then you are probably not very confident. So confidence can also be a product of time. So when people take a long time to make a decision, they will just assume that they're not quite confident. Whereas if they can respond quickly, they are probably quite confident. Alternatively, confidence can be a product of an additional accumulation process after choice. But this post-decision accumulation is something that's only possible with two-stage judgments, where you make a choice first and then confidence judgment. In our study, we are only doing simultaneous judgment of choice and confidence. So the overarching goal here is to test and compare these three approaches. So now we know we can construct different models based on how the approach confidence. But how do we make sure that when we find any difference in their performance, it's due to the difference in confidence mechanism, not other aspect of the decision process, such as noise during the accumulation process? That is, how do we compare the model fairly? So this is the reason why we need to set a common ground for comparison. We chose one of the evidence accumulation models, the LBA linear Ballistic Accumulator, as the framework for all of our models. The family of evidence accumulation models have been generally quite successful with RD and accuracy, but the extension of confidence from this framework is still in its infancy. And that is what we explore in this study. So in LBA, each decision alternative is associated with an accumulator. In each decision trial, evidence begins to accumulate from a random point that's sampled from a uniform distribution with height A. The parameter B here represents the distance between the height of the starting point distribution and the decision threshold. So evidence accumulates with a drift rate V, which is sampled from a normal distribution. The memory strength of the item determines the mean drift rate, and higher drift rate will produce faster accumulation. Oops. Will produce faster accumulation to the threshold. So when one of the accumulator reaches the decision boundary, it triggers the corresponding response, and the response time is determined by the time taken for the accumulator to reach the threshold plus an additional non-decision time for encoding and responding. So LBA does not have within trial noise during the decision process. This means that the race dynamics are determined at the point of initiation. So there are a few advantages of using this LBA architecture. First, the models will be much easier to fit. Second, it will be easier to generalize our models to any number of decision alternatives. And finally, across trial variability in drift rates and starting points, we can capture relative speed of correct and error response as well. So we have now the common ground for testing and comparing the models. So how exactly do we use those three different confidence commutations in models? What would the models be like? So I will start with the direct accumulation approach first. So this model is very similar to the article models that assume confidence itself can be directly accumulated. But instead of differential processes, it uses LBA. So like article, it's assumed that each test item here is associated with a normally distributed level of activation. Mean of the distribution is freely estimated, but the standard deviation is fixed 1 to prevent identification issue. While we previously talked about how this model treats confidence as a multi-alternative decision, right? Now the question is, how do we use this distribution to generate evidence for each confidence alternative? We can get the idea first by looking at a two-choice decision. So what we do is we apply a criterion to partition the distribution into two bins. One for all response and one for new read. The criterion is freely estimated for fixed across target and lowers. The errors on each bin are then translated into true phrase for our decision accumulators. The partitioning we use here is to capture the idea that evidence for the adjacent alternative should be correlated with each other. If we shift the distribution towards the right, we will essentially get more evidence for O, but less evidence for new. So the decision boundaries here can be vary across accumulators to offset an increase in drift rate. Now, if you want to account for confidence responses, we can add more confidence criteria and partition the distribution into more bins. Because confidence options can just be seen as additional alternatives. For a judgment with two levels of confidence, high and low, we can divide the distribution into 4 bins. This corresponds to 4 accumulators for 4 confidence options. The middle ones are for the low confidence options, and also one for the high confidence options. So this accumulator will compete with each other, and when one of them reaches its threshold, we will get both choice and confidence judgments. In this case, we have a high confidence of response. To account for a higher number of confidence options, we just keep dividing the distribution into more bins and have more accumulators. So I will now move on to the balance of evidence approach. The multiple threshold race model is recently proposed by Reynolds et al., which assumes that confidence is computed from a comparison between accumulators. MTR model instead shows the balance of evidence hypothesis by saying that confidence is determined by the difference between the evidence. So larger difference means you have a higher confidence in your choice. For a simple two-choice decision, it's basically the same as the LBM model, where we additionally allowed accumulators to be correlated. The main difference between this model and the LBM model is that it has additional confidence thresholds. So the purpose of having this confidence threshold is to take the continuous balance of evidence and map it onto discrete confidence categories. So to what point can we say we have large enough difference to produce high confidence? For example, for a 4-point confidence scale, there's an additional confidence threshold in each accumulator. In each decision trial, the winner accumulator determines the choice and RT. In this case, it's an O response. So how confidence is derived is by looking at the position of the losing accumulator here. If the losing accumulator has not reached the confidence threshold, then we say it's a high confidence response because we have large difference in evidence. If the losing accumulator has already crossed the confidence threshold, then we say it's a low confidence response. The model is simpler than the confidence accumulator model in the sense that to account for a higher number of confidence options, we don't need to include additional accumulators. Instead, we can just add more confidence thresholds. And finally, there is the timing approach. This is a new model we propose, which only uses subjective time to derive confidence. With an unknown decision, this model is exactly like the basic LBM model or the two-choice MTR model. Two-choice MTR model without correlation. So how it differs from MPR is that instead of comparing the decision accumulators, it uses an additional timing accumulator that serves as a subjective measure of time to calculate confidence. The reason for having this additional accumulator for subjective time is that it is theoretically consistent with the psychological construction of time and the idea that time determines confidence. So theoretical works like Simon et al. 2016 have been using diffusion models as an effective measure to get the sense of time that has elapsed. So that's the reasoning for the time accumulator here. Again, we apply the confidence thresholds to the timer to map out the discrete confidence levels. When the decision accumulator are racing with each other, there's this time accumulator here that keeps track of the time. When one of the decision accumulator reaches its thresholds, and determines on the choice to track the position of the timer for confidence. So same rule is applied here as the NPR model. So if the timer has not crossed the confidence threshold, then it's a high confidence response. But keep in mind that this timer is not tracking objective time. It's instead in the sense of how much time that has elapsed. So even if you stop people at exactly the same time, across different trials, people will vary on how they judge the amount of time that has elapsed. So it's not like within the objective time intervals, say like 500 milliseconds, all the responses people make are all high confidence. So instead you can have slow high confidence responses and fast low confidence responses, depending on how fast you think the time that has passed, which is represented by the timing drift rates. And this timing drift rate stays the same across all similar types. This represents the idea that your the sense of time should be relatively constant, no matter what stimuli you are responding to. So this model is similar to MTR in analysis that you can account for more confidence options by just simply adding more confidence thresholds. Now we know how we can construct different models based on different confidence combinations. The next question is, how can we test and compare the models? Can we put some constraint on one of them and see if their performance differs? Remember, we have this confidence accumulator model that treats confidence essentially as a multi-alternative decision, right? So the classic way to constrain multi-alternative decision-making model is to manipulate the number of decision alternatives. Here we do something very similar. We manipulate the number of confidence options within subjects in recognition memory task. Participants are given either 2-option, 4-option, or 6-option confidence scale to respond with. Since they make decision on their choice and confidence at the same time, this essentially becomes a decision with multiple options. So it was the same recognition task across all conditions, which only differed in how many options participants were given to respond. There was some difficulty manipulations as well. So we've got words with high or low word frequency. Generally speaking, low frequency words are easier to remember and high frequency words are harder. So we thought this could put some constraint on the confidence accumulator model, because as Higgs' law suggests, RT will get slower as the number of alternatives is increased. But in the confidence accumulator model, increasing the number of confidence options basically increases the number of accumulators. By virtue of having multiple accumulators, we can force faster decision because you have greater chance to sample a higher drift rate, which goes against the Higgs law. But just as well as the model ends up doing okay. So this may be because the speed up is balanced out by the way evidence is partitioned. So when you go from 2 to 6 options, you're not just having multiple accumulators that speed things up, but at the same time, you're also partitioning decision evidence into more and smaller bins, which slows things down. So it ends up doing reasonably well. This experiment also provides a validity test for all of our models in a way that they have to capture the complicated two-way relationship between confidence, accuracy, and latency, and changes across different number of confidence levels, while at the same time producing sensible changes in the model parameters across conditions. By sensible, I mean that although there are all kinds of parameters that the model can vary to capture changes across scale, there's no sensible explanation for why the parameters that represent memory strength should change. Also, using what kinds of scale should not affect how strong your memory is for each item. So if you want to say a model is good or valid, they should be able to capture the changes while keeping those parameters, strength parameters, stay constant. So the experiment here uses a centerless memory paradigm where you get will a starter list first, with words presented one at a time. Then decision district the task. And finally, you get a test list. We'll need to tell whether you have seen each of the test items before using one of the 3 confidence scales. So I just told you that there are certain parameters in each model that represent memory shift and therefore should stay constant when varying the scales. You may now wonder, what are those parameters? So in the MTR model, because the drift rate is what's determined by the memory strength of items, constant drift rate across scales give us constant memory representation. Same thing here with the timing model. For the confidence accumulator model, when we compute drift rates, there is this scaling parameter here in the equation. So since the sum of all drift rate is just integral of the distribution, scaling the drift rate differently will suggest a very different level of accumulation. So the scaling parameter here should also stay constant. The original article model failed to keep this parameter constant when capturing changes across different number of confidence options. So now you have all the knowledge about the model and experiment. Let's take a look at the results. For mean RT across conditions, longer confidence scale associated with slow RTs, which is consistent with Benjamin Rudolph's finding. For the mean accuracy across conditions, there are slightly lower accuracies in the longer scale, but the differences are not very obvious. So changing the number of confidence options may not affect performance accuracy. We then use the hierarchical techniques to fit our models. The model selection using WNC values, where with the confidence accumulator model. And with this, we will take a first look at how the models capture the relationship between confidence and accuracy. So the black dots here represent the data. The color stars are the model predictions. The green stars are the MPR model. The blue stars are the Haomin model, and the red stars are the confidence accumulator model. So in two choice conditions, we separated responses based on two levels. So high or low frequency and all or no responses. The fits are very similar here because for a two choice task, all models are very much like the basic Haomin model. In four choice condition, we further separated responses into high or low confidence. So the data here is consistent with the shape of the confidence accuracy curves in research, where low confidence responses are less accurate than high confidence responses. So you get to see this U-shaped curve. All models were able to capture that positive relationship between confidence and accuracy. In six choice condition, again, same U-shaped curves are shown. Overall, the NPR model seemed to provide a better fit, while the timing model and the confidence accumulator model, so the blue and the red stars here, resonated more in the six choice condition. But it's quite hard to judge from this plot to say who is better. So all three models capture the overall relationship. Sometimes one model fits better here, but misfit more in other places. So it's quite hard to say who performs better. So let's take another look at whether the models were able to capture the relationship between confidence and RT. So here we summarize the RT distributions by the 0.1, 0.5, and 0.6 upon 9 quantiles, which represents 10, 15, 19 percentile of the distribution. So we further separated the responses into correct and incorrect ones. Again, in two choice condition, the fits are quite similar. In four choice condition, consistent with first literature, observe faster RTs for high confidence responses. So you get to see this bowing effects here. The three models were also able to capture a negative confidence RT relationship. In six choice condition, again, you see the bowing effects. The confidence accumulator model seemed to fit better overall, while the NPR and the timing model, so the green and blue stars here, tend to misfit more on the point quantiles, especially in this sixth choice condition. But it's also quite clear that all three models are fitting quite well across the conditions. They're all capturing the fast RTs in two choice condition, but and the slow RTs in four and six choice condition. So we're actually quite surprised to see that all three models are performing similarly. The timing model performs surprisingly well here, despite the fact that it's actually more constrained than the NPR model, because we didn't separately estimate the confidence threshold for old and new responses. So you can see here, although the model selection favored the confidence accumulator model, each of these three models have various strengths and weaknesses in addressing the data. For example, the confidence accumulator model fits RT well, but not so much with accuracy, while the reverse is true for the NPR model. And the timing model has its own advantage in addressing multiple alternative decisions, which is not the focus of our study here. And we won't just base all our decisions on model selection. What's more important is whether the model has clear and interpretable parameters. So to look at whether our models produce sensible parameter changes, we additionally allow the key parameters that represent memory strength in each model to vary across conditions. What we found is that the key parameters in each model were only minimally affected when we altered the number of confidence options. So for the NPR model, when we allow all kinds of parameters like the starting point, the decision threshold, the non-decision time, and the drift rate to vary across different scales, you can see that the decision thresholds are really affected by this manipulation, which explains the slowdown in RTs, but the drift rates not varying by much. The mean value are very similar across conditions, especially that error bars overlapping with each other, which indicates that the drift rate essentially stays constant across scales. Same thing here with the timing model. The threshold vary by lots. Although the mean value of the drift rate vary by the bits, but as the error bars are still overlapping, we should be able to say that the drift rate will not largely affect it. And for the confidence accumulator model, you can see the overlapping error bars again in this drift scale parameter. So that also suggests its validity. So all models were able to produce reasonable fits with sensible parameter changes. Now the problem is we haven't found a winner yet. What else can we do? Well, the experiment I just talked about was aiming to place some constraint on the confidence accumulator model in particular. It ended up doing okay. So we therefore turned to the other models and we asked whether we can selectively constrain on them and see how they perform. So we came up with this idea that maybe manipulating the speed, accuracy, and size can constrain the timing model. Basically, what the timing model suggests is that if you respond more quickly, you are more confident. So if you force people to go quickly on the condition where accuracy is sacrificed, the timing model will make a counterintuitive prediction that people will be more confident, which is probably not the case. Also, want to say if the timing model can capture the data when the timer's drift rate is not allowed to vary across conditions. Although many parameters like the threshold, the starting point, and drift rate could all vary to capture speed accuracy trade-off, there's no sensible reason why your innocence of the time will change under different instructions. So this time we're not using words as stimuli because it's quite hard to manipulate accuracy in word recognition. Instead, we adopted a visual recognition task using stimuli we call flashing grids. Here's an example of a flashing grid. So the task here is just to tell whether there are more orange or blue proportions in the flashing grids. So in this one, you can see that there are more orange proportions. So for the experiment, we only use the 4-point confidence rating scale this time, and we vary the instructions and feedback that's been given. So the manipulation was quite successful. When we emphasize on accuracy, we see higher accuracy. When we emphasize on speed, we see faster RTs. And as we expected, when the timer was not allowed to vary across conditions, the timing model performed worse. But this time, the MTR model became the winner. So let's take a look at how the models capture the mean confidence level in different conditions, as that's what possibly distinguishes the timing model from the others. Again, the black dots here represent the data. They separated responses into 3 levels: accuracy or speed condition, flashing grids with more orange or blue proportions, and also correct and error responses. On average, the confidence level was slightly lower in the speed condition. So here are the different model predictions. You can see that the timing model, the blue stars here, is having a hard time capturing changes in confidence level across different response types, especially in the speed condition. This is because when under speed emphasize, all responses were very fast, so the timing model predicts a similar level of confidence. But the timing model is not overestimating the confidence level by too much in the speed condition. This may be because the variations in the confidence threshold compensate a bit for this. So the threshold varying assumption here is somewhat plausible as it captures the idea that participants know that they are forced to respond quickly, so they strategically adjust how they map the time to confidence. Overall, the confidence accumulator model here seems to do the better job. The MTR model, the green stars, is misfitting a bit here, which may represent some compromise in its fit to the large difference between the correct and error responses. So in order for the MTR model to capture the high confidence responses in the correct responses, there has to be a large difference in drift rates between the matching and mismatching accumulators. This means that when the mismatching accumulator somehow managed to win the race, there's little difference in the avoidance accumulated. Therefore, it's more likely to end up in low confidence region. We also did a validity check to see if the timing model can produce sensible parameter changes under different instructions. So we additionally allow the timer's drift rate vary across conditions in the timing model. As you can see, some parameters were really affected by the speed accuracy manipulation. For example, the decision threshold here and the non-decision one, and even the decision accumulator drift rate vary by the bit. But the timing drift rate seems to be minimally affected. Although the mean value vary by the bit, the error bars still overlap with each other, which potentially suggests its validity. Therefore, at this point, maybe it's still too soon to say that the timing model is rejected. Now we are yet to find out which model is the best. There are a few more stairs we are going to climb up in this project. So first, we are trying to evaluate our models based on how well they recover the parameters in each data set. Second, we are designing another experiment that tries to constrain the MTR model in particular by using equal evidence tasks. So basically, we keep the relative evidence between alternative descent, but just vary the level of absolute evidence. So this could be like a brightness discrimination task between two stimuli. They have the same level of brightness, but just across conditions, we allow the overall level of brightness to change. As absolute evidence increases, you can imagine that artists will get faster, but it's possible that we may also observe an increase in confidence. So if confidence is increased, and the NTR model may struggle a bit with this, because increase in the drift rate to both accumulators should not necessarily produce a bigger balance of evidence in favor of whichever wins. While the timing model would naturally capture this, as it predicts faster decision to produce higher confidence. So that's another comparison we can make between our models. But it's also likely that the final conclusion we make here is that there's no winner. Maybe people use all three kinds of confidence mechanism, but just strategically switch between them in different tasks. And that's all my talk. Thank you.